Hey, welcome to this first episode of a new series on modules and dependency management in Java development. If you develop Java applications, or maybe just started in the space, you know that each application is typically composed of many modules. Sometimes a lot of modules. Many of these are open source libraries freely available to use. This is one of the strengths of the Java ecosystem. Many libraries and frameworks can be quickly added to an application by adding a bunch of modules. On the long run though, this comes with maintainability costs and incompatibilities between different versions of libraries and frameworks may cause additional issues. And in your career as a Java developer, you will likely end up in a situation more than once where you work on existing application code that already reuses a lot of modules and where the structure of this is not that clear anymore, which is sometimes referred to as dependency hell or jar hell specifically in the Java ecosystem. Oftentimes I have seen these situations just being accepted as they are, but getting worse over time until eventually they become almost unmanageable and unmaintainable. That's why in this video series I want to dive into what dependency management in Java really means, why we do it and why we need it, what costs come with which decisions, and why are these costs something we need and should accept. But also, what can we do to minimize the risk of ending up in a bad situation, and which tools do we use for which purpose in this context. Here I will, not in this one but in later episodes, talk about the build tools Gradle and Maven, which are also dependency management tools, and want to focus on this aspect of these tools in this series, and also give you a bit of comparison between the two tools in this context. But in this first episode, I would like to focus on Java itself, the tools Java gives us for using modules and for composing applications from existing modules. Although more features for module development and module management have been added to Java itself in recent years, most notably the Java Module System, JPMS, Java had a strong module support from the very first version. It is bound to one of Java's main features, which is developing software independent of a concrete target system. As you may know, the Java compiler does not compile source code directly to machine code, but to the intermediate bytecode format. Here, each of your Java source files is translated into a class file, and then a set of class files is packaged into a so-called jar file. And these jar files can then be executed as part of a program on any system for which a Java virtual machine implementation exists. The Java Virtual Machine, or JVM in short, is what you get when you install Java on your computer. And you run it via the Java command. Now, if we have ready built jar files, we can give the Java command a so-called class path or module path if we use the module system, and give it a list of files. For example, a folder called lib that contains a set of jar files. Java then knows that this is a location to load modules from. In addition, you also give an entry point, which is one class that implements the main method. If you use the module path, this entry point can also be a complete module. Let's look at an example to get a feeling for what features Java itself has to manage modularity and what we need to do ourselves to get a program composed from modules. In the example today, we'll only use already compiled modules, so ready-made jar files. In later episodes, we'll get to how we build our own modules, our own jar files from our source code. But in any case, the example I'm showing now is available on GitHub already, so you can look at the source code and try out things yourself if you like. To work with the example in the video series, I've developed a little tool that allows me to easily switch between different combinations of modules and tools. Also, the tool should help us to visualize some things that otherwise are hidden when you use a normal IDE. In this visualization, each jar file is represented as a gem jar. In this shelf here in the middle, I can select the jars I would like to put into my application. So here I compose an application from modules. Technically, this shelf is a folder on my drive. The folder is called lib, and in the terminal down here, I can use the mentioned Java command to start a Java virtual machine with a class path or a module path that points at this lib folder. So let's put two modules into our application. The example is a small game engine. The engine, called Java Car Engine, consists of two modules, the model module and the engine module. The engine module also contains the engine class as an entry point for the application. So when I put these two modules into my folder and on the class path with that, and now start the command, Java attempts to run this application. However, I don't see anything happening yet. Instead, I get an error from Java itself. It's an error, but you could say it's a feature of the modularity of Java. As I mentioned before, I can combine existing modules freely without having to recompile or relink them statically before. The cost of this is that Java needs to link them when it starts up. In this case, a class called org-slf4j logger factory is used in my code. This means somehow this class was available at the point where I compiled the code of my engine module. But now the class is not on the class path because it is from some other module, and so Java fails to start up. If I am in a situation and I don't use any additional tools like Gradle or Maven for dependency management, I need to go and get the module that contains this class and put it on the class path as well. In this case, it's not that hard to guess what the module is because org-slf4j is a quite well-known logging framework and it's directly in the name of the class. But sometimes it can be hard to figure out which module is actually missing because the error message only tells us which class is missing that could be in any module. This is one of the disadvantages of the traditional class path concept. When Java loads modules, it puts them all together as one big application on the class path, and the information which class is in which module or which code is in which module is basically lost. This is one of the issues Java addressed by introducing the module system in Java 9. The main change here is that a jar file no longer is just a container with class files inside, but has additional metadata, additional information about the module it conceptually represents. For example, each jar file will contain information about a unique module name. So if we use the module system, which we do by defining the module path parameter instead of the class path parameter, this information, if it is available, will be used. And now the error message is much clearer. It first states which module is missing, org-slf4j, and it also tells us why this module is required. Because the module Java Car Engine is requiring it to run. We'll take a closer look at where Java takes this information from in the next episode. Now, with this information available, we can go and find the missing module, for example, by downloading it from the internet and put it into our lib folder. Now, when we run again, we still don't see a running application, but we get more information now on the command line. There's an error, this time not from Java itself, but from slf4j, which tells us it tried to log something, but it has no logger implementation. The flexibility of Java to combine modules not at compile time but at runtime allows libraries or frameworks to separate APIs from implementation and make the implementations exchangeable. This is what happens here. The org-slf4j module, represented by the slf4j API jar, only contains the classes or interfaces to write log statements, which we use in our engine module up here. But it does not contain an implementation of these interfaces that, for example, prints the log statements to the console or into a file. We are free to choose between different implementations when we start the application, and we can exchange the implementations without recompiling any code. Let's select the standard implementation, which is called SLF4J Simple. Now the logging is working and our own game engine is running, which prints log information about something else that is missing for the engine itself to work. Before we fix that, let's just quickly see how we can switch the logger implementation by exchanging a module on the module path. We replace the simple with the JDK 1.4 implementation. This implementation forwards the logging to Java's native logging system called Java Util Logging, which was introduced in Java 1.4, hence the name 1.4. We see that the same information is logged, but is formatted a bit different because this logging system has a different standard configuration. If we would add both jars to the module path, SLF4J will print a warning about this. This shows some of the effects of the flexibility of Java's modularity. We are able to make decisions about which concrete implementation of certain interfaces we want to use as the application developer, even though all the modules we use are third-party. But the cost of this flexibility is that we can have misconfigurations, some leading to an error and some giving us certain warnings. So we have to be aware of these different situations, and depending on whether we use the class path or the module path, the information might be more or less helpful. If we use Java plainly without additional tools, we need to interpret these errors and warnings carefully and resolve them manually by downloading the jar files we want and putting them into the right location and on our module path. So let's continue to getting our example working. The message that is logged here tells us that we need a renderer implementation. This is something I implemented myself in our engine module. So here I also dynamically load an implementation similar to what SLF4J is doing. If no renderer implementation is available, the game engine does not start up and instead prints us this information. Of course, I have one renderer implementation ready based on another existing library called LWJGL. So to run this implementation, I also need the LWJGL modules on my module path. Here we have another interesting situation. Also, in many cases, a Java module can run on any system through the Java virtual machine. There are some Java modules that are dependent on the target architecture. This is often the case for graphic libraries like this one. They include, additional to Java class files, a certain amount of native libraries developed in another language like C or C++. This code can be packaged into the jar files as well and accessed from Java, but then the jar file only works on the corresponding target system. In the case of LWJGL, we have, for example, one jar for Windows and one jar for Mac systems. If I put a jar on the module path that does not fit the system the application is running on, in this case a Mac, I'll get another error from LWJGL in this case. Therefore, I have to make sure to select the module fitting my architecture. It's a bit similar to selecting a certain implementation like we did with the Logger framework, but in this case, I don't really have a choice. So a tool could help me to select the right jar if it knows on which operating system I want to start the application on. But as I don't use additional tools at the moment, I have to do this selection manually as well. And now finally our game engine is doing something and is rendering something to the screen, which we can see here on the left side. In that case, we have only the engine running without a concrete game implementation, so it's just rendering like an empty stage or empty level. As I implemented this game engine with the Java modularity advantages in mind, a game can now be plugged in dynamically just by adding the corresponding modules. So I have implemented a simple game called GemCatch, consisting again of 3 modules, leveraging the ability to modularize my setup. The first module defines the stage or the level of the game. If we add that, we see that there's now some more showing up, like some point counter and some symbols. One feature of our engine is that it can render things as characters if we don't have defined any graphics for our game yet. So we can define and test game without even adding concrete graphics. So let's add the actual game logic, which is defined in the actors module. If we add the module, we again have a situation that we need something in addition, because I decided for this game to use an additional library to define my logic. If I only add the CSV module now, I get an error that the Apache Commons CSV module also needs the Apache Commons IO module. This is what we typically call a transitive dependency. So we add a module and this module already has existing dependencies. We, as a user of the one module, may not be aware of this even. The Java module system helps us at least to know which module is missing. If we only use the class path, the error may be harder to interpret because we'll only get missing classes error. This is another place where additional tools may help us, because now we have to go through each of these errors, find the corresponding module, download it from the internet and put it into our folder, which we also need to do in this case for the Apache Commons Codec module, which is another transitive dependency. Now that we've added all the modules, we might think we are done, but unfortunately we are not yet in this case. Now the application again is trying to start, but we get another error. Again, we have a missing class error. This time also we use the module system. This can happen because when we use third-party module, they are typically versioned. You can see that the jars I've added here all have a version in their name, which means there are multiple, sometimes hundreds of versions of a module. Normally, you can only use one version of a module because they contain similar classes. But in standard Java, it's not possible to have the same class or the same code twice on the module path or on the class path. Now the module system can at least tell us that we have the same module added 2 times in 2 different versions. This is all the module system supports in terms of versioning. It can tell us that I have 2 versions of a module and that this is just not possible, but it can't really help us to tell us which version of a module we need. So this is something we have to manually figure out. And the error we got before about the missing class is because we used a version of the module that does not contain this class. So during development, when the code that requires this now missing class was compiled, a different version was used with the class available. And we have to somehow figure out which one. Let's choose the higher version 2.18 here. And now we see that we resolved the error and our game is running. Here you see how things get more complicated. With the versioning involved, I would like to have more information. For example, which version of Commons IO was used when the Commons CSV version I am using was developed and compiled. This is additional information, also called metadata, that is available for many libraries, but when I use Java plainly, I need to find out where this information is and use it myself to download the right jar file. This is a place where an additional tool for doing this dependency version management becomes essential when the application grows. The most popular tools in the Java space for this are Gradle or Maven, and we'll look at this in the next video. Now we can add the last module of our catch game, which is the assets module that finally adds some graphics. In summary, this rather small example showed the flexibility, the strengths, but also the costs of the modularity concept in Java. We have seen different issues we may run in when we use existing modules. But you also have to see that using all these modules allows us to build applications quite quickly without redeveloping everything from scratch. If you want to take a look at the source code of the example, which I link in the description, you will see that there are not many lines of code written. Most of the functionality is in the open source third-party modules I'm using here. Now, if you scale this up to a business application, you reuse much more existing functionality from a framework like Spring or Spring Boot for web application development. And you typically also encounter different instances of the problems I showed in this episode. This is why we use additional tools for dependency and module management. How these tools help us to identify and solve these problems easier or partly automatically will be covered in the next episodes. We will start next time by taking a closer look at a single module and see what's inside the class file and which additional metadata is available in which places and can be used by which tools. By this, we'll also take a look at how dependencies between modules are defined, from which Java is able to produce the missing module errors. See you next time.